Today we first discuss about Lagrangian and Hamiltonian of a relativity particle. If the screen is visible, hello.
Yes, sir. Yes,
Okay.
sir.
Okay. Okay.
Yes, sir.
As you all know, the special theory of relativity, which was first given by Albert Einstein in 1905, after the and if a particle is moving with a velocity comparable to the speed of light, we consider as a relativistic particle. And here we want to find the Lagrangian and then Hamiltonian for a relativistic particle. Okay. And you know, E is equal to mc square is a famous equation which was derived for relativistic particles, and it is applicable to any other cases. E is equal to mc square, where E is the total energy and m is the mass of the particle. Okay. We know momentum is mass into velocity, but in a relativistic case, mass, if a particle is moving, then its mass is no more a constant. Rather, it varies with velocity, and if m0 is the rest mass of the particle, then m will be m0 by 1 minus v square by c square root over. Okay, so if m0 is 0, there are many particles having rest mass 0, then what will their moving mass? Hello? If m0 will be 0, then what will be m?
0.
0. But one condition, when v is equal to c, then what happens? It is 0 for other cases, but when v is equal to c, then what will this term? Square root of 1 minus v square by c square is equal to? For v is equal to c, v square by c square is 1. So square root of 1 minus v square by c square how much? Hello?
It will be 0, sir. 0.
0. Total denominator 0. So here 0, 0 by 0. Isn't it? If v is equal to c, then it is 0 by 0, which is non-zero. 0 by 0 is how much?
Infinity. Infinity.
Infinity, not exactly infinity. It may be any number. Suppose let's say it is x. So you know that is from this equation 0 by 0 is equal to x. Then 0 is equal to how much? X into 0. If you take cross product, the 0 is equal to x is 0. So when x is multiplied with 0, it gives 0. Then what is the value of x? It may be 1, maybe 2, maybe 3, maybe anything. Okay. Have any value, maybe finite, any finite value. Okay. So for v is equal to c case, this mass m is non-zero. So we use when a massless particle is moving, then we consider if it is moving with velocity with speed of light, then it has some effect mass, you can say resultant mass or anything, and due to that it has in other properties, momentum, energy, everything. Not it. For example, photon rest mass is 0, m0, but it moves with velocity of c, so it has a mass when it is moving, and it has a momentum, and it has a energy. We know energy is h nu. Okay, so we can say it m is equal to h nu by c square, because energy is equal to mc square. So it has energy, mass will be h nu by c square when it is moving. So mass is not 0 always. When it is for a moving photon, it has some mass. Here for any other massless particles, if it is moving with velocity c, then it has some mass. Okay? Hello?
Yes, sir.
Yes, sir. Yes, sir.
So this is a very important equation for actually give the. Okay. Then we go to our topics. Now we know that Lagrangian is equal to kinetic energy minus potential energy. Okay. And total energy of a body, which is actually for a conservative system, is equal to Hamiltonian, is equal to T plus B. For a free particle, what is the Lagrangian? Free particle means there is no force. Free. It is free. Free particle, no force. So no force means no potential energy. Because force is equal to negative gradient of potential. If force is zero, potential is zero. So for a free particle, actually total energy is kinetic T. Okay. And you know general kinetic energy T is equal to half mv square. Half mv square kinetic energy. Okay. Okay. Or if it has a potential energy, then it half mv square minus v. But E is equal to T plus B. So I can write actually T plus B means half mv square plus V. Okay. So in general, I can write T plus B mv square minus half mv square minus V. Okay. Can I write this? T plus B. T is equal to half mv square. So in half mv square, I can write mv square minus half mv square. Isn't it? If I write one step here, T plus B, I write first mv square minus half mv square. Then plus V. Now I slightly change, take minus common here, so it will be half mv square minus V. Because this quantity is your L and mv square, I can write, we know mv is equal to P momentum, so I can write it as a P dot V. It will be mv into mv square minus L. Okay, this one. So energy for a free particle can be written as P dot V minus L. Isn't it? Hello?
Yes, sir.
P dot V minus L. Okay. But energy is equal to how much? mc square. So in place of energy, I write mc square, and P is mv. mv into V is equal to mv square. So mc square is equal to mv square minus L. mc square is equal to mv square minus L. From this equation, we can write L is equal to how much? L is equal to this, go to, and this becomes M, L is equal to minus mc square mv square minus mc square. From this equation, you can take L this side, so mv square minus mc square. Okay. So L is equal to m common, taking common v square minus c square. Clear? From this equation, but we have a equation mass for relativistic body. Mass is not actually varies with velocity as m is equal to m0 by 1 minus v square c square root over. So if I use this, then this m all into v square minus c square will become this value. You can check this. Oh. Now, but m is equal to how much? M is equal to m0 into 1 by 1 minus v square c square root over. So if I put here, so it will be our m0 divided by square root of 1 minus v square by c square into v square minus c square. If I calculated 1 minus v square by c square, so if I take this c square, it will be c square minus v square, c square root over o. When you go to numerator, it will be m0 c. So m0 c v square minus c square by square root of c square minus v square. Okay. But we know square root of c square minus v square into square root of c square minus v square is equal to c square by v square. So it will be actually m0 c, since it is v square by c square, taking minus common, it will be c square minus v square, and denominator is root over of c square minus v square. So cancel, it will give you the root over. So it will be minus m0c square root of c square minus b square. So Lagrangian for a relativistic particle is minus m0c c square minus b square root over. Okay. If you add potential, or if the particle is moving in conservative potential field, then we add potential L is equal to T minus V. It is only kinetic energy term. Okay. This is only kinetic energy term. So it will potential energy with kinetic energy minus potential energy. This is the Lagrangian for a relativistic particle. Here, current doubt. Hello? Third question is coming. What is the Lagrangian for a relativistic particle? Hello? Clear?
Sir, move ahead, sir.
Huh? Okay. So next we calculate the Hamiltonian. Okay, this in non-relativistic limit. Actually, this gives you this value because for non-relativistic limit, V is most less than C. So this equation can be expanded. Okay, and that is, you know, this term will be minus m0 square into 1 minus v square by c square to the power half. This we have left this term, only this term. This will be this. If this quantity is most less than 1, v by c is most less than 1, we can expand binomial expansion. You know, 1 plus x to the power n. When mod x is less than 1, is equal to 1 plus nx plus n into n minus 1 by 2 factorial into x square, that mods. And here expanding and neglecting higher terms, we first term becomes minus mg square is present. We expand only this term 1 minus this. So it is here n is half. So it is, and x is minus v square by c square. The term will be 1 plus nx, 1 plus half into v square by c square. Okay. Then other terms, but since v by c is much less than 1, so its square will be more less than 1. Suppose v by c is 0.01. If you take its square, its square will be 0.301, much smaller. So we can neglect that. So for non-relative limit, in place of this, I can write this, and this is basically minus m0 c square and this term, and half c square cancel. Okay, here is minus minus, here 1 minus n x, minus minus plus half m0 v square. So in non-relative limit, this gives this Lagrangian. Okay. Then go for Hamiltonian. Once the Lagrangian is known, it is fairly easy to derive the corresponding Hamiltonian because using our formula, we know Hamiltonian is equal to summed over Pj Qj dot minus L. Okay. So once we know the Lagrangian, we found this and this Pj. Or if you want to say P, this quantity Pj is equal to how much? Del L by del Qj dot. Qj dot means velocity. So here for a free particle, we have a Hamiltonian actually P Q dot minus L. Q dot means velocity V minus L and P is equal to del L by del V. Okay, we use this P is equal to del L by del V. Lagrangian is given. We take the derivative. We found it will be m0 v by 1 minus v square c square root over. Because derivative of 1 minus v square c square root over. It will power half, so half into to the power minus half means 1 minus v square 1 by 1 minus v square by c square root over into minus 2v minus minus plus. Okay, so derivative will this much. Uh, and using this formula, Hamiltonian PV minus L, we found Hamiltonian will be P dot V minus L, putting this value and multiplied V. So P dot V, uh, you know, okay. And another thing is, we know Lagrangian is a function of Q dot T, and Hamiltonian is a function of QPT. In Hamiltonian, all V should be replaced by P. And so from this equation, you can calculate V. P is equal to m0 V by this. So squaring both sides, we found P square is equal to m0 square V square by 1 minus V square C square. So from this, we found V is equal to this much. P by m0, simplifying, 1 plus P square by m square to the power minus half. Or putting this in place of V, and here P is equal to this V and minus L, we found H is equal to square root of P square C square plus M0 square C4. Similarly, if potential is present, H is equal to P square C square plus C4 plus VR. You also know this. This is your E. In relativistic theory, E square is equal to P square, sorry, not T square is equal to P square C square plus M square C to the power 4. 0 square C to the power 4. Also by this way, putting these values P, V and L, you can get the same equation. Okay. This is the Hamiltonian for a relativistic particle. So syllabus is written and find the Hamiltonian for a relativistic particle. This section is clear? Hello?
Yes, sir.
Okay. Next we go for another important section, Liouville's theorem. Okay. Actually, Liouville's theorem tells that in phase space, the density is conserved. We will discuss the motion in the phase space. Phase space motion. The density is a conserved quantity. Phase space means position momentum space. It is 6 n-dimensional space for the n-dimensional particle. For one particle is 6-dimensional space, 3 position coordinate and 3 momentum coordinate. The dynamical state of a system at some instant of time can be represented by point in phase space. The motion is we can plot the phase space, and in phase space the path represents the exact path of motion, because here the momentum is given and from momentum you calculate energy, and here position q gives position. If you know its position and energy, then we got the exact path. The point will not be stationary but will move along a definite trajectory. So a point or system point moves in the trajectory. We already discussed that. And we know actual from Hamilton's equations, position and momentum coordinates, which are known as canonical coordinates, they are related through Hamilton's equation of motion or Hamilton's canonical equation of motion. Qj dot is equal to del h by del pj and pj dot is equal to minus del h by del qj, where h is the Hamiltonian of the system, which is a function of Q1 to QF and Q1 to P. F is number, is degree of freedom, means 3n minus k. A normal system where k is the constant, no constant, F is equal to 3n. Or in some books, F is equal to n. Written. As a result of this motion, the density of the system in phase space changes with time. Rho changes with time since particles are moving or system points are moving in phase space, and then density. Okay, density actually number density. Number of phase points per unit volume. Number of phase points per unit volume which may be changed. Uh, for this rho phase density, actually Liouville's the theorem. According to this theorem, mm, the first part, the main theorem, the conservation of density in phase space. In phase space, the density is conserved quantity. That means derivative of rho with respect to time is zero. Del rho by del t is equal to zero. And there is also another extended part. The conservation of extension in phase space is zero. And the space, the extension space, or a phase space is gamma is the space, and the extension is del gamma. Then del gamma variation with respect to time is zero. Del gamma is a constant quantity. The volume of the disposal of particular number of phase points is conserved throughout the phase space, which meaning is the volume at the disposal of a particular number of phase point is conserved throughout the phase space. Phase volume is conserved. Okay, then proof, first part proof which is important. So consider any fixed element of volume of phase space. Phase space means it has n number of position coordinate or f number of position coordinate and f number of momentum coordinate. So here space has q1 to qf and p1 to pf coordinates. Let us consider the change in one direction in q1 and p1 case. So q1 here phase points, we consider the volume between Q1 to Q1 plus delta Q1. Other Q components remain fixed. And similarly for momentum coordinate, we consider uh, the points between P1 to P1 plus delta P1, other momentum components fixed. So the number of system in the located in the volume, actually volume of the total phase space will be delta Q1 to delta QF into delta P1 to delta PF. Changes at the coordinates and momentum of the system vary. In a time dt, the change in number of the system within this volume of phase space will be in a time the number of phase points, actual number of phase points changing is given by del rho by del t into delta t. It is the change in rho with respect to time into volume. Volume is this one. So to change is density with respect to time to volume. For one part is this, so for whole volume it will be integrated. Okay. Whole volume. This change is due to the number of systems entering and leaving the volume in the time dt. Okay. This is the change in number. So actually this is outgoing minus incoming. Change in number means outgoing minus incoming, or incoming minus outgoing. It is positive, then incoming is more, incoming minus outgoing. If it is moving more from a output is more, then it is outgoing minus incoming. Okay. This change is due to the number of systems entering and leaving the volume in time dt. Consider two faces of the hypervolume normal to the q axis with coordinates q1, q and q1 plus delta q1. Consider the particles they are coming through this side and leaving through this side. Isn't it? So if there is a surface, particles are coming through this side and leaving through this side. So consider this. So number of phase points entering the first phase in time dt, the number of points entering here will be how much? Will be change in q1 like this formula. Okay. Rho dq1 by dt into dt. Here change in density del rho by del t into dt. So here dq1 by dt into dt. Then other variables, because q1 variable is left here. So rho into, because it depends on density also. If it more dense, more particular number will be more. If less dense, the number will be less. So it change in q1. The particle passing through this region will be dq1 by dt into change in time dt. This is for change in time dq1 by dt, which is q1 dot into dt, and then multiply the rho, and besides q1 other volume element del q1 to del pf, where rho and q1 dot density and indicate a component of velocity. The number of phase points entering the second phase actually through this, how is it leaving number of, it will be how much? Here in place of q1 I write q1 plus delta q1, here q1 dot. So here q1 dot plus delta q1 dot, which is written q1 dot delta q1 dot is written like this, del q1 dot by del q1 into delta q1, variation. It is variation just. So variation in the delta q1 dot by delta q1 delta q1. Okay. Similarly, in place of rho, here density is rho number of particle, but rho plus here that will be how much? Del rho by del q1 into del q1. In q1 delta q1, how much now? How many number of particles are present? It will be depends on density variation del rho by del q1 into delta q1. So in Q phase, but number of particles are entering are this much. For this side, Q1 plus delta Q1 number of particles leaving will be this much into dt for this, and this variables or integration. Now the number of phase points remaining in the region will be this minus this. The extra will be 2 minus 1. Okay. This was if you multiply these two, actually first row q1 dot, second will be del rho by del q1 delta q1 into q1 dot, this one del rho by del q1 into delta q1 dot, third one will be del rho by del q1 delta q1 into del q1 by delta q1, another row into this rho into del q1 dot by del q1 into delta q1, this term. Third is q1 dot into this, which is written here, and fourth term, this second in this second. It is ordered del rho by del q1 into delta q1 dot by delta q1, delta q1 into delta q1. Delta q1 is very small, and delta q1 and delta q1 is much smaller than that. Suppose it is 0.01, what I am telling, and again it is 0.01. So when we multiply, it will be 0.30 into 1. So we can neglect this term when we add with 0.01. Not actually 0. I am telling. Suppose let's 0.301. So again it is 0.301. So what will be the result? 0.701. So when you add 0.701 with 0.301, it will nearly equal to 0.301. So it can be neglected. Okay, so I can neglect the fourth term. Okay. Neglecting higher order terms, it was written there, means power of delta q1 2 is neglected. So we have only these three terms, and taking common delta q1, I can write like this. Oh, okay. Okay, can you derive this or not? Any problem? It is important. Liouville's theorem is very important question. Only how much particles are or number of phase points are entering through q1 and how much are leaving through q1. When entering q1, you are considering this surface, so only q1 rho q1 dot. When leaving this surface, here q1 is q1 plus delta q1. So in place of q1, I have to write q1 plus delta q1. Means q1 derivative means delta q1 plus delta q1 derivative, which is q1 dot plus delta q1 dot by delta q1 delta q1. Second thing is density. Here is rho, and here rho plus due to variation of delta q1, rho plus del rho by del q1 into delta q1. Okay. Now multiply these two. There are four terms. One term is neglected due to delta q1 square. Three terms are remain here in this equation. rho q1 dot for rho del q1 dot by del q1, q1 dot by del, and del rho by del q1 into delta q1. Clear? Hello?
Yes, sir, clear.
Okay. Then from this equation, actually we have to derive the exact form of Liouville's theorem. Now, using the equation 1 means this one, rho q under this, the number of points entered here. Okay. And this is the number of phase points leaving the system. Equation 1, number of phase points entering the system, because equation 3 is simplification of equation 2. Okay, so total number of phase points remaining in the system will be equation 3 minus equation 1. By subtracting these two, what you get? You see rho q1 dot here, rho q1 dot, another term is cancel. Only this second term multiplied with the volume element will present. So second term, when we subtract it from, okay, remaining in the system means incoming minus outgoing. You know it. Remain in the system, incoming minus outgoing. So incoming minus outgoing, because that is a minus sign. That reason will be this much. This term minus sign. Similarly, it is for Q1 change. For P1 coordinate, we have similarly, if you can write for this P1, number of entering through P1, number of leaving through this. In here only, instead of Q1, we have write change is P1. So whatever here Q1 is replaced by P1. Rho Q1 dot into rho P1 dot Q1 dot P1 dot, other things remain same. So for P1 coordinate, we can write like this. This is the number of phase points stay in the phase space. So now the net increase in time and the number of system in volume phase space is then obtained by summing the net number of systems entering and the volume through all phases. It is one position phase, this is one momentum phase. There are f number of position phases, f number of momentum phases. I'll add all these things. So finally this is addition, which is divided delta n number of phase points, minus taken here, j is equal to 1 to f, so it will be qz or this term. If you add these two, rho taking common, del q1 dot by del q1 plus del p1 dot by del p1. Again here q1 dot del rho by del q1 of p1 dot del rho by this means j. I take the dummy variable j, so some rho j is equal to 1 to f, and this is the equation. Isn't it? Equation 6.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
But what is the change? The change in the phase point d by dt of delta n should be equal to del rho by del t into delta t into volume element. Whatever number of phase points changes, it is the gives you phase density, because density is what? Rho is equal to, number density means number per unit volume. Is phase, we take a particular phase space. Okay. So a number is how much? From here definition, know n is equal to rho into v. Isn't it? Hello?
Yes, sir.
Or
Yes, sir.
change suppose del rho. Del rho means I can like, or delta rho. Delta rho is delta n by v. So obviously delta n is equal to delta rho v. Okay. This is written here. Delta n variation with respect to t, take derivative, will be time del t derivative, del rho by del t delta t. This is volume element for that space. Hey, volume element is in three-dimensional space, dx, dy, dz. This is the volume element. Smaller. So here for 6n dimensional space or 2f dimensional space, del q1, del q2, del qf into del p1, del p2, del pf. with the volume. Volume into rho. This is we know that. Now substitute this. So left hand side is equal to this del rho by del t into del t into del q and del qf del q into del pf. Or right hand side is this. You see one term will cancel. Uh, but this term when you check this one del qj dot by del qj dot is equal to del h by del pj and pj dot is equal to how much? Minus del h by del qj. Please substitute in this equation. So what here del by del qj in of qj dot means del by del qj dot of del h by del pj, which will be equal to del square h by del qj del pj. Is not it? Similarly for this one, del by del pj of pj dot means del by del pj of minus of del h by del qj. So putting that we finally find minus of del square h by del pj del qj. If we add these two, this will be how much? Del square h in numerator, denominator del qj del pj or del pj del qj. Either you take with respect to qj, pj are independent variables, so this will be same. So if we add these two, it will be how much? Hello? If we add, we have written del qj dot by del qj plus del pj dot by del pj. Put qj dot is equal to del h by del pj here. Pj dot is equal to minus del h by del qj here. So this is equal to how much? Del qj by del qj means it will be del square h by del qj by del pj. Is not it?
Yes, sir.
It will be minus del square h by del pj. So plus minus, if we add this, it will be give you plus minus I will be give you
Zero.
what? 0. So this term actually give you 0. So only we found del rho by del t is equal to minus of sum rho j is equal to 1 to f del rho by del qj dot plus del rho by del pj dot. This result is known as Liouville's theorem. Because if you take one side, then it will be del rho by del t plus summed over this. Okay, del rho by del qj dqj by dt plus del rho by del pj dpj by dt. This meaning is actually it is d by dt of rho when rho is a function of qj pj t. Is equal to 0. You know that if f is a function of x, y, z, then df by dt will be how much? Del f by del x into dx by dt plus del f by del y into d and dy by dt plus del f by del z into dz by dt. Is not it? Hello?
Yes, sir.
So from this we found del rho by del t is actually 0, which is the Liouville's theorem. This is the formula. So we got the first part of Liouville's theorem, conservation of density of in phase space. Okay. That means the density of a group of points remains constant along their trajectories in the phase space. If at any time the phase points are distributed in uniform phase space, they will forever have uniform density. We go to second part. Second part, del V, d by dt of
So,
del V is equal to 0.
so
Uh,
what are the application of this theorem? So, is it applied in the flux also or liquid?
Oh, that is continuity equation. What we are telling, that is your same thing, continuity equation. And for a fluid, we have a continuity equation that del rho by del t plus del dot j is equal to 0. That's called continuity equation. It is similar to continuity equation, but it is in phase space because here not the fluid in phase space particular. And when we assume position momentum space, and that space phase density is a constant. Not exactly the continuity equation, but when we consider a fluid flowing in classical or quantum mechanics or fluid dynamics, to come through this equation, for and that is known as continuity equation. Del rho by del t plus del dot j is equal to 0. Here we are not considering the j part. Here we only consider the phase space. So del rho by del t is 0. But a fluid rho is the density and j. Okay, any fluid you can consider the charge. We call it charge density and current density J. Or okay, quantum
So,
mechanics also you see this equation, continuity equation.
here the density is meant for the this.
Phase space. Here density of phase
Okay.
space. Number of phase point per unit volume. We are considering only phase space. We are not considering any flow of fluid.
Okay.
Then second part, the extension in volume is a constant, so its derivative is 0. Because we know, as we discussed, n is equal to rho is equal to n by b, so delta n is equal to rho db. So if take its derivative, it will be del rho by del t into delta v plus rho into d by dt of delta v. Okay. So since the number of phase points delta in a given region of phase space must remain fixed, the system can neither be created or destroyed. Okay. So no, there is no source or no sink, what we call. So whatever enter, it should be leave the system. There is no source or sink inside the phase space. That means the variation of delta n with triam is equal to 0. It should be always constant. That means this term will be 0. But we have already proved that d rho by dt is equal to 0. So what it means? D by dt of delta v must be 0. This is the principle of conservation of extension in phase space. But this one is your Liouville's theorem. If you will ask, you can also prove the second part. It is clear? Very important.
Yes, sir.
Okay. Then we go for next section, Hamilton-Jacobi theory, which was written in action angle variable case. Okay. Why we actually study this Hamiltonian formalism? We know Hamiltonian is equal to T plus P. Okay. And there are Hamilton's equations. We call canonical transformation from small pq to capital PQT. Why we actually study is what is our aim here. Canonical transformation may be used to provide a general procedure for solving mechanical problems. Mainly two methods are followed. One first method is the Hamiltonian is if the Hamiltonian is conserved, then a solution could be obtained by transforming to a new canonical coordinates that are all cyclic, thereby providing new equation of motions. You know, in the canonical transformation, the form of Hamilton's equations are same. So if we want to transform one coordinate to another coordinate system where the coordinates are cyclic, then we easily can get the equation of motion. Another thing is, in second approach, it need to search canonical transformation from our old coordinate to new set of coordinate, which may be all are constants. We have some values or initial values. Constant means initial value is given. At t is equal to t0, the value is q is equal to q0 called initial value. Or t is equal to 1 value is initial value. So constant. So we can transform all coordinate to a constant coordinate. Then we can easily get the equation of motion. The okay. So we can transform our old q to a new q, so that q is a function of q0 p0 t cap small p function of q0 p0 t. It is p0. Okay. And by taking this idea, actually Hamilton's Jacob equation, one equation are developed known as Hamilton's Jacob equation. We already know that if you transform q small q to capital Q, then capital set also satisfy the Hamilton's equation. If k is the Hamiltonian there, then qi dot capital Q del k by del pi, and pi dot is minus del k by del qi. And another equation is k, okay, k is equal to h plus del f by del t. F is your generative function. We already discussed in previous classes that. Okay. Let's say for k is equal to 0, we consider that the new Hamiltonian is 0. Then what happens if k is equal to 0? Then our old Hamiltonian is equal to minus del f by del t. F is your generative function, or h plus del f by del t is equal to 0. Let's for simplicity take is the f2. Why f2? Because for f2 is commonly used. F2 is a function of small q and capital P. Let's say simple q1 1 p, small q and capital P. Then if our function is f2, then qi will be del f by del pi. According to our formula in generative function, pi is equal to minus del f by del qi. Because this small q capital P is known, so we have to calculate small p capital Q. Okay. So, and Hamiltonian h plus del f2 by del t is equal to 0. And h is a function of q and p. We know Hamiltonian is a function of q and p. So, in small q, q1 to q, and in case of small p, I have to write del f2 minus. If minus, then function means we can take plus. F of minus is same as f of x. Value is. Okay. Minus del f2 by del qi, del f by q1, q2, qn, t. Okay, I can write in place of pi this. So if these are constants, I transform in such a way that this it gives a coordinate or new pi are constants. Then I have only, if these are constant alpha, alpha 1, alpha 2, alpha n, it will be only n plus 1 variable. These are constants. If we take these set constants, and this equation is actually known as the Hamilton-Jacob equation. This equation consider partial differential of n plus 1 variables. Then the solution can be denoted as S, known as the Hamilton principal function. So if we take those things constant, then we call it as a Hamilton's principal function. Hamilton's principal function is a function of position coordinate, and where momentums are constants. Okay. Suppose that X is the solution, so S is equal to q1 to alpha and t, which is known as Hamilton's, this equation, Hamilton's principal function. Okay. From this function, actually, what is the important? These things are not required. Only remember this is the Hamilton's Jacobi equation, and this f is actually your Hamilton's principal function. What are the importance of this S? Okay. So here f2 is S. Only thing is f2 is S. So you calculate pi is del f by del qi, so you can calculate del s by del qi, and capital Q is del s by del pi, but pi is equal to alpha. We choose small pi is a constant alpha written here. So the two equations are this. If it is a constant alpha and s is a function of q alpha t, if you take derivative of alpha I, then we get a new coordinate beta I. Beta is obtained from the initial condition simply by calculating the RHS. alpha and beta. This is a procedure. So finally, we got Q and P in terms of alpha and beta in terms of constants. Here, our aim is to transform in such a way that we got new coordinates are constant, or we can express our old coordinates in terms of constants. The procedure. Main thing is in a syllabus written the this principal function, Hamilton's principal function and the significance. Hamilton's principal function is S, which is basically a function of q to qn and alpha 1 to alpha n t. And what is its physical significance? Its physical significance is if you take its derivative, since it is a function of q, alpha and t, then ds by dt will be del s by del qi into dq by dt, del s by del, okay, del alpha I, d alpha I t, t del s by del t. But dqi by dt is qi dot, and since alpha is a constant, d alpha I by dt is equal to 0 plus ds by dt. Again, S is f, we know pi is equal to del f by del qi or del s by del qi. If you put this, it will be pi qi dot plus del s by del t. But again, h plus df by del t is equal to 0. We said k is equal to 0. This is k. If k is 0, it is 0. That means del f by del t is equal to minus h. Del f by del t is equal to del s by del t. So del s by del t it is minus h. So ds by dt is equal to p sum dot p q dot minus h. That means the quantity is your Lagrangian. We know from definition L is equal to sum dot pj qj dot minus h, or h is equal to sum dot pj qj dot minus L. So the ds by dt is Lagrangian. Its physical significance it is a Lagrangian. So s will be how much? Integration of L dt plus constant. So your s principal function is nothing but you can calculate by integrating L Lagrangian dt. Okay. So Hamiltonian function or principal function at more time integral the Lagrangian only by a constant. So integration of Lagrangian by a constant. When Hamiltonian does not explicitly depend on time, this s can be written as it is a function of q alpha t. You can separate variable. You can write the w q alpha minus alpha t. When Hamiltonian does not depend on time, so we can separate the time into term, and this wq called Hamilton characteristics function. Okay, one is s is Hamilton's principal function and w is Hamilton's characteristic function. It is equal to s is equal to w minus alpha t. The physical significance of w you can calculate if you take a total time derivative dw by dt. It will be sum dot del w by del qi into qi and plus alpha derivative with respect to alpha d alpha by dt is 0. So it is pi. So if pi is equal to dw by del qi, you know that. So dw by dt is equal to sum over pi qi dot. So w is equal to integration of this pi qi dot into pi dq by dt into dt. This is a p which is a action. Nothing but abbreviated action. Okay. So these two are written the Hamilton's, one is characteristic function, another is a, Hamilton's principal function. Okay. And what is principal function and its physical significance? Okay, any doubt? So S is principal function and ds when you calculate this, or find its significance, you have to take a derivative, which is actually Lagrangian. ds by dt is Lagrangian. Any doubt? Hello?
No, sir.
It is a simple function. Okay. But it's important you solve many problems by using this method, Hamilton-Jacobi method. For example, harmonic oscillator is particularly harmonic oscillator is written in syllabus to solve in many ways. And so one way is you can solve this Hamilton harmonic oscillator problem by using Jacobi method. For Hamilton harmonic oscillator, you know its potential energy is half k q square because force is proportional to minus x or minus q if q is the coordinate, and if it and potential energy will be in force in negative gradient of potential V will be half kq square. Okay, because F is equal to minus del V by del X or minus del V by del Q. Suppose you take a constant k. If F is equal to minus kq, then what is the value of V? Will be half kq square, because you have kq square, take a derivative, 2 to cancel kq minus kq. Okay, so potential energy for harmonic oscillator is half kq square, and kinetic energy is, you know, half mx dot square or half mv square, which is equal to p square by 2m. And this k constant, spring constant, or which is related with an angular frequency, w is equal to k by m root over. You already know that plus 2. So W is equal to k by m root over. If you put that, Hamiltonian for a harmonic oscillator is p square by 2m plus half m omega square q square. From this Hamiltonian, I have to get the equation of motion, or what is the value of q. Q is how much, p is how much. Okay. For a conservative system, we know Hamiltonian total energy using Jacobi equation, where p is equal to del s by del q, and substitute the Hamiltonian. Using the procedure, that is k is equal to 0, k is equal to h plus del f or del s by del t is equal to 0. That means, okay, putting this, so p is equal to how much? Del s by del q. P square will be del s by del q square by 2m plus 1 by 2m. This already put here. Here in place of p, you put del s by del q. We got this. Oh, so 1 by 2m taking common, we write this is the equation h. But h is equal to how much? Minus del s by del t. From this equation, h is equal to minus del s by del t. Minus del s by del this, or this plus del s by del t is equal to 0. This is the equation. Since the explicit dependence s on t is involved, only last term, a solution can be written alpha t. There is no t here in the Hamiltonian. When Hamiltonian t independent, we can write like this s as wq alpha minus alpha t, like the procedure. So if you write in place of s wq alpha minus alpha t, then del s by del q will be how much? There is no q here, so del s by del q means del w by del q, and del s by del t means there no t here, minus alpha. Okay. Hello? Are you
Yes,
getting
sir.
my point or not? Oh.
Yes, sir.
So put only, very easy written, everything was written here. So you put here and w alpha. Okay. Here del w by del q. Putting these two, we got del w by del q square m square is equal to alpha. Or del w by del q the square is equal to 2m alpha minus m square omega square q square. Or del w by del q is equal to its root over w is equal to integration with respect to dq. If you integrate this, a constant go outside the integration, and this integration dq. Okay. But s is equal to our wq minus alpha t. So this integration wq minus alpha t final. So if you integrate this, s is equal to root m. You can integrate equation, but we are interested to calculate the partial derivative s with respect. Okay. So we proceed as follows. S is equal to how much? Here 2 root alpha, 2 root alpha cancel. Root over of m into dq 1 by m square q square minus alpha t. But del by del s alpha is another beta constant. So root m dq, if I take its derivative with respect to alpha, beta is equal to how much? Del s by del alpha, take its derivative with respect to alpha. So if for alpha, then this term will be derivative with respect to alpha minus t. If you take its derivative, it will be dq by 2 alpha m minus m omega square q square, half into 2 cancel. So this one minus t. Why I write this? Because this we can integrate this function. It is very difficult to integrate this one. It gives a form on 2 alpha. If you take 2 alpha root 2 alpha common, then I like this dq by 1 minus some a square q square. Put x is equal to that m omega square q m omega square by 2 alpha root over into q. That means beta plus t is equal to this one. Beta plus t will become, if we substitute here, this is x square. I mean substitute, this is x square. So correspondingly dq will be calculated. Dq will be this one. So these are the constants, because integration of dx by 1 minus square sin inverse x or sin inverse this. So I found sin omega beta plus t is equal to sin inverse omega m omega square 2 alpha into q, or q is equal to 2 alpha by m square sin omega beta plus t. Okay, we found the position. Similarly, p is equal to del s by del q, which is del w by del q, and integrating this derivative in w with taking 1 by 2 m this, we found p value will be this, and putting q value sin this one, we get the value of p. Okay, so p q can be found for a harmonic oscillator, and p q were this for a harmonic oscillator. It is one way to solve the harmonic oscillator problem. The other problems are given, we don't need that. Okay, in a syllabus written harmonic oscillator problem, you can solve it anyway. It is one method I am discussing here. Other methods are also available. Okay. Then go for principle of. This section is clear?
Yes, sir.
Hello? We go for
Sir,
principle
we
of.
will need the study material, sir. I request you to kindly provide the study materials for future
Yes,
examinations and
yes,
all.
yes. I will send these materials. So,
Sir, thank you so much, sir.
next one is the principle of least action. It's one of the variational principle. Actually, what we see in case of Hamiltonian formulation, there are many paths between 2 points. So suppose a particle is moving from 1 point to 2 point, uh, there are many paths is possible. Okay, in a normal configuration space, okay, many paths are possible by the time, but for exact path of motion, we know the integral L dt will be a constant. I, this one, no? Or delta variation is equal to 0. For exact path of motion from point 1 to point 2 is equal to 0. Variation 0. We know already this uh, from Hamilton's principle. Okay. Now consider a path which is slightly varied from the actual path. For actual path, we satisfy this equation. Slightly vary from the actual path. We also discuss in it in our Hamilton, when we discuss about Hamilton's equation or Hamilton's principle. Actually, Hamilton's principle. Let us consider. Suppose it is moving from one time t1 to t2, a path. It followed a path which is slightly different from actual path, a delta variation from actual path. Or we consider, we can suppose it actual path is your qt0, then that path will be qt a function of alpha eta t, but the endpoints are same. For all path endpoints are same, t1 on starting t1 and t2. Okay, so endpoints are same. That means this term eta it, when t is equal to t1 it is 0, when t is equal to t2 it is 0. Okay. And for second thing is, for exact path alpha is equal to 0. This is the thing. Alpha is a parameter, goes to 0 for the exact path, and function eta I necessarily have to vanish at the endpoints. Clear? So we can take another path. It is the exact path, and when both are same, then alpha is equal to 0. but endpoints of both are same. That means that t is equal to t1, both are same, and t is equal to t2, both are same. Then that means that t is equal to t1 alpha. It I t is equal, because it's t dependent quantity. It I is 0 and t is equal to t2, it I also 0. Okay. Now two. So we take this one, the delta variation of it's not actual path, slightly above or below the actual path, delta variation. So now the delta variation of the action integral, L integration of L dt. If you take delta variation, this integral is known as action integral, integration of L dt. So I can write like this, L dt. It's for actual path. When it is from deviate path, then t1 plus delta t1, and it is t2 plus delta t2. Then it depends on alpha, L alpha dt minus L0 dt. When alpha is equal to 0, actually the actual path L0 dt. So it is, and this contains the deviation. Clear? L alpha dt is equal to L dt plus L0 dt. Think it. If you take this into left and this come to right, and this come to like to left. If you take the left, it is actually L alpha dt. This is total path. T1 plus delta 1 or T1 plus delta 2 is equal to path, exact path T1 to T2 plus a variation path. This so variation path is equal to means change. Change in path is equal to new path minus old path. This is going to change. When suppose this is your actual path, this is your new path. Delta variation means the change. This change. Change is equal to new path minus actual path. And for if second new path is actual, then alpha is equal to 0 by definition. Alpha 0 means you put your L0. L0 minus L0 dt is equal to 0. So no change. L alpha means the integral evaluated along the varied path, and L0 is the correct corresponding refer to the actual path of motion. The variation is clearly composed of two parts. One arises from the change in the limits of the integral to first order infinite. This part is simply the integrated on the actual part times the difference in the limit. The second part is caused by the integration of the varied path. Now between the same time limits as the original integral, we may therefore write delta variation. Okay. If I integrate it, this will be taking delta variation. It will be delta of L dt t1 to t2, Lt to delta t2 minus Lt1 delta t1 integration. If you integrate L alpha t, if you take it delta, so opposite t, so it will be Lt2 delta t2, t2 t means for L at that point. I will integrate it t L alpha t, t varies from delta t2 delta t1, imagine that. So it will be L t delta t2 minus L delta t1, and this integration L dt. Actually delta variation for actual path, delta L is equal to 0. No variation, so we can write like this, delta L dt t1 to t2. Here the variation in the second can be carried out through a parameterization of the varied path, exactly as per the Hamilton's principle, except that the QA does not vanish at the endpoint. Okay. Now the endpoint of integration, this integration delta L delta t, if you see, this will be delta L. Okay. Delta L by del qi minus del t by del qj dot delta qj dt. We have already, when you derive the actually Lagrange's equation from Hamilton's principle, we get this equation. If you see, actually this equation is taken from there. When we derive the Lagrange's equation from Hamilton's principle, delta L dt is equal to this one, del L by del qi minus dt by delta q dt, del q dt, for del I calculated for del qi. from which point you calculate that if delta L this is 0, exact path this is 0 and this bracketed term is 0. This is your Lagrange's equation. For exact path of motion this was 0, so this one 0. Obviously LQ dot 0 delta variation for exact because this term is 0. At endpoint variation are 0, so this term gives 0 and if this is 0, this is 0 and this is Lagrange's equation. When we derive Lagrange's equation from Hamilton's principle, we use this equation. By Lagrange's equation, the quantity in the square bracket vanishes. This if you put this 0 and then delta variation take the form delta of LDT is equal to LDT plus PI, this one, del L by del QI dot is equal to PI delta QI. 1, 2. Okay. It is just change. So if delta T is 0, it will be 0 where LDT. This is our exact equation. Delta LDT is equal to this plus delta LDT. From here, when we calculate this delta LDT, we found this is your from Lagrange's equation. This is 0. So only this quantity del L by del QI dot delta QI dot. So I write here del L by del QI dot delta QI dot. So finally delta we found L dt. L delta t. This is nothing but L delta t. Delta t2 minus delta t1 L delta t. So if I can write it as L delta t limit from t1 to t2. Then meaning is same. T is L delta t2 minus L delta t1. So I write this. Okay. This term is 0, so this is the equation. Are you getting my point or not? Hello? Hello? Hello?
Sir, author please.
Here, delta of L dt is equal to this one. Right. Now I simplifying this term, delta L dt. We derived in when we derive the Lagrange's equation from Hamilton's principle, we check there is an equation like this. Only derive this. Okay. Alright, and F is written in place of L there. Delta F del T is equal to del F by del QI, del F by del QI dot, and del F by del QI dot. In place of L, it was written F in there. You see, this is the equation. If you take delta L, because L is a function of Q, Q0 dot and T. So then you write delta L del L by del QI into dQI dt, del L by del QZ dot and del QZ dot by del T, del I by del T into del T. Del T will be 1 del L by del T. Okay. Then you take this variation and we found this. It was already derived. Okay. But now this bracketed term is your Lagrange equation dl by del dqi minus d by dt del L by del qi dot is equal to 0. So we put 0 here. So fine, we got del L by del T is equal to only second term. But here del L by del T is second term plus this equation L delta T minus L delta T1. I can write it as L delta T at T1 T2. Isn't it? When I put this, when T is equal to T2, L delta T minus L delta T, like limit. I can write in terms of limit. Isn't it? Hello? This equation can be written like this or not?
Yes, sir. Yes, sir.
Then from here I got this term. Combining these two, I write like L delta plus Pi del L by del Qi total is equal to Pi. Pi delta Qi 1 to 2. This is one. Okay. Delta Qi refers the variation of Q at the original point T1 and T2. We would like to express the delta variation in terms of change delta Qi between Qi and the end points of the actual path Qi at the end points varied. Okay. But delta Qi is actually del Qi small variation plus Qi dot into del T change due to T. Qi dot means dQi by dt. And this equation, if you put this in place of delta Qi is equal to delta, so delta Qi is equal to how much? Del Qi is equal to delta Qi minus Qi dot by del T. So Pi into delta qi one term, and p minus pi qi dot delta another term. So putting this here, I got this equation. Okay. But here see, this quantity is L dt is equal to, if delta t taken common, so it will be L minus pi qi dot. It is what? We know Hamiltonian is equal to pi qi dot minus L. Sum obviously, qi dot means your sum actually, present everywhere. Pi qi dot minus L. So L minus this equal minus h. So I write minus h for these two terms. Taking delta t common into minus h, so minus h delta t. This is pi del qi. Okay, to get the exact principle of least action, we consider three important considerations by three important qualifications. Only systems are considered which L and H are not explicit function of time. Since it is a more conservative system, and conservative system Lagrangian is independent of time. Okay. So also Hamiltonian is independent of time, and consequently is a conserved system. Second thing is the variation is such that H is conserved on the varied path as well as on the actual path. Hamiltonian is conserved for both the paths, actual path and varied path. Third, the varied paths are further limited by requiring the delta qi vanish at the endpoints, but not delta t. So delta qi will vanish at the endpoint. At 1 and 2, delta qi is equal to 0. Using this, we can write equation 8.77 reduces to delta L dt is equal to minus h, because this will be where endpoint, it will be 0. Delta qi at 1 is equal to 0, delta qi at 2 is 0. This is basically pi delta q1 delta q2 minus delta q1 pi delta q1, but delta q1 and delta q2, this term is 0. So this 0 0, it will be minus h dt 1 to 2. H dt 1 to 2 means h into delta t2 minus t1. Okay. This is, we got this equation. But under some condition, this action integral itself becomes, but the integration of L dt, we know L is equal to pi q dot minus h. L dt will be pi q dot dt minus h. H means time t1 to t2. It is basically integration of h t1 to t dt t1 to t2. Since h does not contain t, so h is a constant, so h into dt t2 minus t1. So because L is equal to pi qi dot minus h. So we integrate it with t, pi qi dot t, h dot dt integration h t2 minus t1 it gives. So now delta variation, multiple delta, for delta of L dt will delta pi qi dot dt minus h delta t2 minus delta t1. Comparing these two equations, here we found left hand side L same, here this term same, so we have an extra term, this should be 0, and which is your principle of least action. So delta pi q dot dt t1 to t2, it should be 0. Clear or any doubt? This is very important, derive the principle of least action. Hello?
All good, sir.
Okay.
Sir, what type question will come?
Derive the principle of least action. Or discuss briefly about principle of least action. Any question? Okay. Then we go for this is principle. Last one is action angle variable. One type of variation method for 1 degree of freedom systems. Actually, this is for a periodic motion system. We already discussed in the previous classes about periodic motion, and there are two kind of periodic motions: libration and rotations. Okay. New here variable j designed to reflect the transform of okay. J, which is known as action variable, it is integration of p dq, integrated over a closed path. We call it known as action variable. But the integration to be carried over a complete period of libration or rotation. It is for a periodic motion. Okay. So the one this is one type periodic motion. Another periodic motion is exactly rotation. Earth is rotating around the sun is a periodic motion. And we have in some cases creating periodic motion. Okay. This is called libration. It is rotation. From Hamilton-Jacobi theory, we got this equation: S is equal to W minus alpha t, and Hamiltonian H is minus del S by del t, and P is equal to del S by del Q. We got these equations there. We will apply this. Okay. So let's say H is equal to alpha. Consider H is equal to alpha. So J can be written as a function of H or alpha. Like H is equal to alpha. So J can be written as a function of alpha, where alpha is H. Or you can reverse, in reverse way you can say H is a function of J. From Hamilton's characteristic function W, what we will discuss, WQJ, the generalized coordinate conjugate to J. J is momentum. The generalized coordinate conjugate to J is known as action angle variable omega, and it defined by the transformation equation omega is equal to del W by del G, del J. J is your action integral. We can write J function of H or alpha, or reverse way H is a function of J. So, or alpha, what is WQ alpha can be written as a function of WQJ, and the variable corresponding or conjugate coordinate corresponding to J is known as your action angle variable omega. So this is Q, that is P. So it can be derived as W is equal to del W by del J. Now the equation of motion can be written as Q dot. We know Hamilton Q dot is del S by del P. So W is playing the role of Q. Since it is a momentum, J is momentum, it is Q. So Q dot del S by del P. So W dot will be del S by, in place of P, I have write J, del J. Is also written as nu J, frequency. W dot nu J. So W will be nu T dt, or W is equal to nu T into beta. The change in W as a Q goes through a complete cycle. So if you calculate delta W, it will be del W by del Q into dq. But del by del Q, W is equal to small w, sorry, del omega. Small w means it omega. Omega is equal to nu T plus beta frequency. And taking its delta variation, delta W will be, and we can write del W by del Q into delta Q. It is varying over whole path. But this one, as omega, is equal to dW by dj, or del W by del J. Putting that, we got this equation, which is del square W by del Q del J. And since J and Q are independent variable, we can write del W is equal to del by del J. We can take, since the integration is only on Q, so I can take del by del J outside. Del by del J, integration of del by del Q into dq. But del W by del Q is equal to P. So it is nothing but integration of P dq, or P dq means J integral. But del J by del J, 1. The W changes by unity if Q's go through a complete period. Okay, change will be 1 if you go through a complete cycle. So that del W will be 1 means we know nu into tau, frequency and time period. Frequency is inverse proportional to time period, you know that. Nothing new is there. Only thing is you calculate frequency as del H by del J. W dot of frequency can be calculated by derivative of Hamiltonian with respect to J. There are many problems for this. Suppose harmonic oscillator problem. Hamiltonian given an action angle P dq integration, you write action J. So here from this equation you can write the P. But H is equal to alpha. So P is a function of 2m alpha and this. So J is equal to put, and you know the Q value. Then if you put the Q, then you calculate the J. Okay. J will be found be 2 pi Z by omega, or you can calculate from frequency nu del H by del J from formula. We found this. Okay. These are too many problems to solve this. You have to remember nu is equal to del H by del J. Suppose like this problem. Here a particle in one dimension, this Vx is this, and if total energy is, then find its time period. H means total Hamiltonian total for a conservative system. How to calculate time period? The formula is frequency del H by del J, so time period is inverse of that, del G by del H. J is equal to P dq. Okay. So P0 Q0, you have to know its phase space. Then you calculate all this. And this is for only for problems. It will be not written in our syllabus. If you face any further exam, if you give further examination, either appear for net or gate, that type of questions are comes to solve problems. Okay, but the syllabus it is not written, so don't worry about this part. Okay. So any doubt from any sections? Okay. Only one last class will remain. I will take tomorrow, 4 to 6. What we left for phase space, we'll discuss there, or Poisson bracket if anything left, then we'll discuss tomorrow. Okay, any doubt?
No, sir.
Sir, any online sessions are there, sir, for IIT or NPTL?
Hmm.
Uh, is there any online session are also there supporting? Anything you things are
Online? No, in NPTL there is classical mechanics course. Actually, in NPTL there are two sessions. One started with January and other is July. You have
okay?
to register there, and it is a 3 month course. You have to
Ne-
free to register, and you will take all classes and videos.
Okay. Otherwise, things are good. Like we have to understand, sir.
Okay.
Take classes are good, sir. Thank you, sir.
Okay. So, shall I leave?
Sir, how can I get the materials, the study materials, sir?
Um, but I am teaching. I will send all this material in your group.
So I think we will create a all physics students. We want to create a WhatsApp group, sir, and will you interact there, sir? That will be better, I think.
There are you have created many groups. So to 2 3 groups already you have created.
Amresh, you please send your number, then people will connect, join you in the group.
Can you please write my number? Actually, I am new here and I'm joining the classes from last 2 days. So I don't have any contact with any physics guys here.
You send your number in the message, people will help you.
The admin will add you. You just send your number.
In
Okay, okay,
message.
okay.
In message.
Okay. Can you please share your number? Can you please?
Amrish, in the message tab, you can send your number, put your number in message. In the Google Meet itself.
So I am leaving. Okay. We'll meet tomorrow.
Sir, kindly share today's PDF,
Yes, yes, yes. I
whatever.
am sending in all my classes. I am sending my notes. Okay.
Okay, sir. Thank you, sir.
Thank you
Thank
so
you so
much, sir.
much.
Thank you so much for the nice class, sir.
Okay.
Okay, guys, I have sent a message. My mobile number. Please add me in the group.
Kader.